Today I'm talking about the polymers for liquid crystal alignment. In the first case, I will talk about what is LCD and the principle of edge operation, and very briefly introduction, and I will talk about the synthesis and characterization of two types of polymer. The one is the loving type material, and the other one is non-loving type, the photoresponsive type material. Its name is 6F-HAB, 6F-HABCI. It means polyimide main chain and the cinnamate side chain to align liquid crystal using the photoreaction. Yeah, firstly, the question is what is LCD? So nowadays, everybody knows what is LCD, but today I will define LCD as a liquid crystal. Crystals are activated by electric field to produce the display imaging. In here, I talk the liquid crystal. The image, as shown in this figure, in natural state, the solid state goes to isotropic liquid state by heating. But in a liquid crystal, it has one more phase. That is this metal phase. That is the mixture of the crystalline solid state and this isotropic liquid state. So we can define this liquid crystal as a molecules that have some of a long range order of a solid, but the freedom of motion of a liquid. So this slide shows how can LCD can be operated. As shown in here, the LCD consists of two cross-polarized transparent panel, and the liquid crystal is existing between of these two cross-polarized panel. And when voltage is applied, the liquid crystal is aligned like this. So in this case, the light source cannot pass through this cross-polarized panel, so we can see the image or not. So nowadays, the liquid crystal display is nearby our common light. This is a simple calculate, and this is the simple watch, and the laptop notebook monitor. And nowadays, everybody has this LCD monitor in your home, and the LCD TV, and the personal game console. The liquid crystal displays application is very huge. So if you have the strong and very sharp knife, you can, if you cut the liquid crystal display panel, you can see this cross section. So today, some present talk about this TFT and organic TFT, and some present talking about the color filter. But today, nobody talking about this the alignment layer. So it has a good chance to present about alignment layer. So this alignment layer is very important. Why? Because the alignment layer is direct contact with the liquid crystal and align and control the liquid crystal alignment. So in common industrial field, the LCD, the liquid crystal alignment layer, was prepared by loving process. Loving process means using this loving roller and just the simple buffing the polyimide surface using this buffing roller. So this loving process is a simple process. So we can realize the high thermal stability and the high anchoring energy and the proper tilt angle. And in common case, the polymer layer was used by polyimide because of this polyimide has the high thermal stability and high chemical resistance. So we synthesize a lot of polyimide. The polyimide has the alkoxy panel oxy group as a side chain, and we synthesize the polyimide has an alkoxy side group, and we have published the macromolecule or the Journal of Polymer Science. And also we synthesize the polyimide. It has the steel band side chain, and also we synthesize and characterize the polyimide, the copolyimide. And today I will be talking about this polystyrene system, because this polystyrene system is a simple chemical structure, and the liquid crystal was aligned perpendicular direction to the rubbing direction on the rubber polystyrene film with a zero reduced angle. So it's a very interesting thing, because in common case, the liquid crystal is aligned the parallel direction of the rubbing direction. But in this case, polystyrene is on the polystyrene film surface, liquid crystal is aligned to the perpendicular direction of the rubbing direction. So firstly, we measure the AFM. This image is the unrubbed films AFM image. As shown in here, the RMS surface roughness is 0.32 nanometer. It means the unrubbed polystyrene film is very smooth. But after rubbing, we can see some scratch along the rubbing direction. This white arrow is the rubbing direction. But interesting, we can find one other thing. The direction, you can find some groove-like structure like this along the rubbing direction. It means in case of a polyimide, you cannot find this phenomenon. Only the polystyrene shows this the regular groove-like surface topology. And you can see here the surface roughness across the rubbing direction is 2.7 nanometer, and along the rubbing direction is 3.0 nanometer. And also we measure the optical retardation of polystyrene, the rubbed polystyrene film. In this case, we can know the information of polymer chain orientation using the optical retardation. As shown in here, the retardation is decreased as increasing rubbing density. It means the polystyrene is the negatively bi-represent film. In other words, the polymer main chain was along the surface direction, but the paneling is aligned the perpendicular direction of the surface. And we measure the polarized FTIL using rubbed polystyrene. As shown in here, we can see anisotropically aligned the paneling segment and the polyvinyl segment. From this polarized FTIL, we can obtain one thing. That is the rubbed polystyrene film surface. Panelings are preferentially reoriented into the plane perpendicular to the rubbing direction, but the polymer chain is aligned along the rubbing direction. And also we measure the reflection FTIL. As shown in here, the red line is transmission mode FTIL, and this blue line is the external reflection mode. In this case, we can see the external reflection mode has more intense signal. It means the polar direction of panel side groups are on average aligned nearly normal to the rubbed film surface, like this figure. And we fabricate the liquid crystal cell, and measure the liquid crystal alignment behavior. As shown in here, the liquid crystal, in here we use the 5 CV liquid crystal. The liquid crystal is aligned perpendicular direction to the rubbing direction with the gyropoid tilt angle. So conclusively, I can conclude one thing, that is on rubbed polystyrene film, the panelings are reoriented plane perpendicular to the rubbing direction, and the polymer chain is aligned rubbing direction. And the 5CV liquid crystal is aligned using the pi-pi interaction between this paneling and the measuring unit of the 5CV. And next one is the non-rubbing type, the liquid crystal alignment method. In case of the rubbing process, the rubbing process is the directly physical contact process. So it can make some problems such as dust generation, and the rubbing process can destroy the TFT by the electrostatic charging. So in order to overcome this this shortcoming, some people developed a new way using the UV light. So the method can be characterized this three ways. The one is photodimerization, the other one is photoisomerization, the last one is photodegradation. So in order to reveal the mechanism and the pre-tilt angle or something, I have synthesized a lot of the polyimide. The polyimide has the azobenzene side chain, and this polyimide has the photoreactive group in the main chain. And we have the synthesized the soluble polyimide. It has the steady-pyridine group and coumarin group and cinnamate group and the alkoxycinnamate group. Today, and also I synthesized the polyamide, and it has the photoreactive group in the main chain, and the side chain type, the polymer, and also the polyester. It has the main chain type, and the side chain has the different alkyl chain lengths to control the pre-tilt angle. Today, I'm talking about the 6F-HABCI. It means the polyimide backbone is the 6F-HAB, and the CI means it has the cinnamate group and the side group. As everyone knows, that this cinnamic acid undergoes the photodimerization or photoisomerization, and finally the isomer goes to photodimer like this. So firstly, I synthesized use 6F and this HIV unit by one-step method, and we measure the thermal property. The degradation temperature is 40 degrees C. It means it has the high thermal stability, and we can obtain the high molecular weight. And using the 6F-HAB, I synthesized the 6F-HABCI using this cinnamoyl chloride. After the synthesized the photoreactive polyimide, the degradation temperature is 340 degrees C, and the gas transition is 181 degrees C. It means after the introducing side group of cinnamate, this polymer has the highest thermal stability. And we measure the photoreactivity using the polymer film, the irradiation using unpolarized UV light. As shown in here, before UV light irradiation, the film exceeds absorption maximum at the 278 nanometer, but upon the irradiation energy, this peak decreases like this. It means in the film system, this cinnamate group causes the isomerization or dimerization. And also we measure the FTIR, after irradiation, the unpolarized UV light. As shown in here, some peaks are changed like this. The characteristic peak is the 1633 and 981, the Kais. It means this two peak comes from the binding group of the cinnamoyl moiety. And one more thing is once the 1737 Kais becomes weak and broad, it means the corresponding to non-conjugate to carbonyl stretching. Conclusively, it means the loss of pi conjugation due to the photodimerization of a side group. So we think this photosensitive polyimides undergo photodimerization under irradiation unpolarized UV light. So in order to confirm the photoreaction in the film, we measure the solid state NMR. As shown in here, this is the solid state NMR before the UV radiation. This is the after UV radiation. As shown in here, the very small and very broad peak appeared at around 47 ppm. This is coincide with cyclopentane carbon. So we can combine one thing. In the film state, because of the UV radiation, the film undergoes photodimerization. And we measure the optical recognition using the polyimide film irradiated by linearly polarized UV light. Before the experiment, we used the unpolarized UV light, but from here we use the linearly polarized UV light, and we can see the retardation value is increased with the increasing exposure energy source. It means the polyimide chain is aligned because of the induced by the linearly polarized UV light exposed. And we also measure the polarized FDIR. As shown in here, we measure the two peaks. The one is the 1633 Kaiser, and the other one is the 1376 Kaiser. In this case, we can know the information of the polymer chain orientation, and in this case, we can know the photoreactivity. As shown in here, this absorption band align the perpendicular direction or polarization direction of the linearly polarized UV light. It means the parallel direction position that this moiety is consumed more rapidly than other things. And from this band, we can know one thing: the imide NC bond are oriented by linearly polarized UV exposed to alignment perpendicular to the polarization of the linearly polarized UV light. It means this polyimide main chain is oriented by exposure of linearly polarized UV light. And also we measure NEXAPS. This NEXAPS data give us information about the very near surface, the polymer chain orientation. As a result, we can see the polymer main chain reorientation by linearly polarized UV line. And also we fabricate a liquid crystal cell, and the liquid crystal is aligned this direction. So I can conclude two things. The one is the polymer chain is reoriented by the exposure of linearly polarized UV light, and the linearly polarized UV light can align the liquid crystal on the polyimide surface. Okay, thank you for your kind attention.